Okay, how are you all? We will finish today talking about collagens and the rocket example. Then we will start talking about the rotation of the rigid body, the angular position, the angular velocity, and so on. Now I will start solving an example on an elastic collision, but in two dimensions. In elastic collision, we talk about the full inelastic collision. We have two objects, for example, two cars, two balls of clay. The first one is moving in positive y direction, the direction, this direction. We have this. This is the first mass, I think. Mass A. Better to name. And with velocity VA. And we have another object, MB, with velocity V to the positive x direction. At the origin, they collide. Then they move in one direction and this direction with an angle from the positive x-axis. And they stick together. Both of them come to be just one object. This is the object A and this is the object B. And they both have velocity v2. From the equation of the collision, we know that we are talking about the inelastic collision. The kinetic energy is not conserved. We have, before the collision, we have ma multiplied by its velocity va as a vector plus mb multiplied by its velocity is equal to the total mass after the collision, which is ma plus mb multiplied by the final velocity after the collision. If we have given that ma equal to how much? 900 kilograms, and the velocity VA is equal to 15 meter per second in J direction, upward, as we see. And MB is equal to 1800 kilograms, it's a bigger car, and its velocity VB in I direction is just 7 meters per second. Any question about that? Online, any question? I'll put the chat. Okay, thank you. Now let us apply the numerical values. We need to find the velocity after the collision as a vector. We need also to find the direction of that velocity. We need to find this theta or phi angle. It is easy to be found. Okay, MA, it is 900. We know how to apply the numerical values now. VA is 15 in J direction, plus MB is 1800 multiplied by the velocity, which is 7 I hat. This will be equal to the total mass, which is 19 plus multiplied by the velocity v2. I will divide it to x component and y component as we see. This will be equal to V2 in x direction I have plus V2 in y direction J hat. It is simple. Now 15 multiplied by 19 J direction, I'll put it like this. I hat and we have J hat. The J hat momentum, this is all together mass multiplied by velocity, which is momentum. It is 13,500, and this is equal also to 12,600 kilogram meter per second, the unit for that. This will be equal to, in x direction, it is 900 plus 1,800, which is 2,700. V2 in x direction, I have plus the same number, which is 2,700. V2 in y direction, J hat. Now we have two components. One of them in I direction should be equal to the y I direction in the right hand side. So we have 2,600 is equal to 2,700 V2 in x direction. Also, the second component we have 1,500 should be equal to 2,700 V2 y hat. From these two equations, we can find that V2 in x direction, and we can find V2 in y direction. V2 in x direction is 4.76 meter per second. And this is equal to 5 meter per second. This is in x direction and this is in y direction. Now we find the components for V2. It is in x direction. V2 in x direction equal to 4.67 meter per second, almost 5. And also 5 in y direction. We need to find this angle phi. We did this many times before. Okay, we have the velocity Vy is equal to 5, and also okay, it's okay. And we have Vx equal to 4.67 meter per second. We need to find the total velocity. We can find it. V2, we can find the speed. V2 is equal to the square root of 4.67 squared plus 5 squared. And we can find 5. This is 5, which is tan inverse, as always, of the y component over the adjacent, which is the x component of the velocity, which is 5 over 4.67, which is almost 45. It is it is 46.975 degrees. Any question about that? Why? It is just simple. It's very simple. We just take a velocity in y direction and velocity in or a momentum in y direction, a momentum vector in x direction, and we add them together. Then we find the momentum after. We see that the x component of the momentum is conserved, and the y component of the momentum is also conserved. That's it. Now, as I told you from before, I will talk now about the rocket problem. We will see a new source of the force, which is not the acceleration. We know that the force is equal to m multiplied by the acceleration. But now, this is A.6, the rocket example. It is just an example, okay? We know that the force in general is equal to ma, which is m multiplied by dv by dt. But if we enter the mass inside the time derivative, this is velocity. This is the momentum, as we know from before, as a vector, if the velocity is a vector. But now we assume that the mass is constant and the velocity is changeable, and the change in velocity with respect to time is the acceleration, which is the force. Now the force is equal to dp by dt, as we know. This is the general form of Newton's second law. Because if the mass is changing, then the force is equal to, I need to differentiate the momentum. How can I do that? I need to differentiate the first term, which is dm by dt multiplied by the velocity plus the mass by dv by dt. So this is the general form of the Newton's second law. In general, we know this term, this new term, related to some examples like the rocket. Because I will show you now. For the rocket, there is the mass of the rocket. This is the mass of the rocket. And there is some material, gases, go out from this rocket with constant velocity. So this V exhausted materials. And these materials, it is the mass of these material. It is, for example, 100 kilogram per second. So it is delta M. This is delta M, exhausted mass. It's going out during delta time. So this mass is not constant in general. It is going out from the constant mass or the main mass. Now, we have a force. backward direction. We have a force for the exhausted materials. This force acts on the rocket mass and do a reaction force forward, and this force acting on the rocket. So the rocket going under this force. Any object going under a force, it will accelerate and it will not have a constant velocity. Then this rocket has acceleration, not a constant velocity. But the exhausted materials from here come out with constant velocity, but with changing mass. Now, we will not talk, we are talking about one term, not the second one. We are talking about just this first one. We will solve this term for the exhausted materials. The force source is the change in mass. So it will be the same thing. dm exhausted by dt multiplied by its velocity. This for a time dt. Maybe you can write it also if you like. It is delta m over delta t. But when delta t goes to 0, it will be dt. Okay, any question about that? So this is our force. The direction of this force is downward, as you see. This is the action. And the reaction is applied on the rocket upward. We are talking about the motion just in one direction, in y direction. Maybe we can't, if I draw this experiment in x direction, we can talk about it in x direction. We are talking just about in one direction. So the force acting on the rocket comes in this form. It is the change in mass during a time multiplied by the velocity of this exhausted materials. This force will be exerted on the will be applied on the rocket, and it will be equal to the force on that rocket, but upward. So this is all of our formula need to be applied. The force on the rocket, it is simple. It is equal to m of the rocket multiplied by the a of that rocket. The mass of the rocket, I can give it to you. The acceleration, you can find it. Any question about that? We'll solve an exam. Any question about that online? Here in the class? Okay. Let us solve this exam. Okay. This is our rocket. It ejects 700, so delta M of the exhausted material is equal to 750 kilograms every minute. So delta T, how much delta T? It is 1 minute. How much 1 minute? 60 seconds. Okay. The velocity of the exhausted material is V of this exhausted material is equal to 85 meters per second. Okay. Calculate the forward thrust, the force. I need to compute now the force. I have all the givens now. I need to compute the force on the rocket. I can compute the force of the exhausted material. I need just to use this formula. F of the exhausted materials, as you see, it will be to the negative x direction, right? It will be equal to delta M over delta T multiplied by the velocity. All of this for the exhausted materials. This will be equal to delta M is 750 over 60 multiplied by 85. This will be equal to 1,000. Yes. 62. Newtons. So the force is 1,062.5 newtons in negative x direction. Okay. I can't see the negative sign. I can use the negative sign for the v, because the velocity now it is in negative I direction, right? This is the velocity in negative x direction. So I can put a negative sign here, and the force can be in negative direction. But we are physicists now. The minus sign, we need to know that meaning that sign, which is the direction. Okay, now, what is the force on the rocket? It is equal to the force for the exhausted material, but with the negative sign because the direction. So the force is equal to 1,062.5 newtons to positive I direction. So this rocket will move, will accelerate to the positive I direction, x direction. If I give you if the mass of the rocket is 20 tons, what is the acceleration? The acceleration is the force on divided over the mass, as we know. It will be equal to, it will not be that high, it will move slowly or accelerate slowly. Meter per square second. That's it. So, if this rocket is outside the Earth's atmosphere, there is no need to any air there to make the exhausted material push on that air to move the rocket forward, because we have, from the beginning, we derived the force by differentiating the momentum, because we have a conserved momentum backward and forward. So because of that, the rocket will move forward, the boat will move forward, the ship will move forward, and anything, because the conservation of linear momentum. Linear means, we will talk about that now, means motion in straight line. Any question about that online? By the way, I upload final chapter, which is chapter 8, homework on mastering physics. And I think I put almost 2 weeks to finish it. But if you need more time, it's okay. You know, there's no problem, no issues with the time for homeworks. Any question about the previous material? The linear previous material. Can I erase? Okay. Let us remember our study from the first to the sixth. We talk about the displacement. This is the x line. For example, this is the 0. This is the negative direction. We talk about the displacement from x1 to x2. This is the displacement delta x, which is x2 minus x1 in a straight line. It is linear. If we take it during delta time, we can find, for example, the average velocity, which is delta x over delta t. It is a linear velocity. It is a straight line velocity. If we have 2 or more velocities, then we can find the acceleration average, which is delta v over delta t, because it is acceleration on a straight line. It is a linear acceleration, just what we compute for our rocket. And we work and we compute the linear momentum. Also, we compute the work, which is the force with dot product with delta x. All of our physics quantities comes in straight line, even in x or in y or in z direction. We now, in physics, not just have one direction of motion or one shape of motion. We have many shapes of motion. For example, the door is closing with an angle. This motion is linear, but this motion is not. I change the angle of this vector. This is a vector. Also, this motion is rotation. Okay. We apply the rotational motion many times in our life, each day, even in our legs, when we are moving, or with our hands, right? Now we'll talk about this. We'll solve some examples. We need to know the relations. It will be simple. We just will remove x and y and z, and we will use the angles, theta or phi. We have angular position and velocity and acceleration. As we from before, we have linear position, which is x. From before, the position was x of t as a function of time. And we have the velocity is v, and the acceleration is a. Now, the position, if we have the x, y coordinates plane, this is x, and this is y. And we have a point, this point. We can represent this point from before by the vector r, as we know, and this vector is equal to rx and ry. We are moving a straight line in x direction, and we move also a straight line in y direction. Then we reach that point. But we have another representation to that point. If we have this r and we just move this r from, I will not use the xy components now. I will make this r sleep and lie on the x direction. This is r, and just I move it in rotational way like this. I will move this vector using an angle. I can name this angle theta or phi or alpha, any name I need to name it. So this point now, its position is r and theta. I have another theta. For example, if I have another vector, for example, this. So this is theta, another theta. I can name it theta 2. This is theta 1. Okay. So if I start from the origin and I move my vector with angle theta 1, then theta 2, then theta 3, I can move any theta I need. Sometimes when I move my theta, I can be fast. Sometimes I can be slow. Sometimes I can be accelerating or decelerating. Then now I have theta tells me the position or the angular position. The angular position, it is not x now. It is not linear position. It is angular position. I use theta. I have angular velocity. I will name it omega later. So because I have rotational motion, if I have a motion, then I have time. If I have motion and time, then I have velocity. My motion now is angular. Then my velocity or my speed is angular. Also, if I have change in my velocity, then I have acceleration. And this acceleration is not linear, it is angular also. Is that understood? Now, let's remove the linear. There. example, 30 degrees. 30 degrees. We will use the radians system. The radians system will be used. We have, this is, if I need to draw an angle. This theta is equal to 0 degree, and it is equal also to 0 radian. This theta equal to 90 degrees, which is equal also to pi over 2 radians. This angle is equal to 180 degrees, which is the same to pi radians, which is pi. This angle is 270 degrees, which is equal to 3 pi over 2 radians. And the total angle, which is 360 degrees, is equal to 2 pi radians. What is the radian? It is another system just to talk about the angles. These are the main angles, but what about one radian? For example, we need to find how much 1 radian. Okay, if we need to use these numerical values to find 1 radian, we have 180 degrees is equal to pi radians. Pi, as we know, is equal to 3.14 radian. It is the same. So this is equal to 180. So this is a 3 and 14%. How much 1? So okay, I need to find how much 1 radian. It is equal how many degrees? Just I need to cross product between them, which is 180 multiplied by 1 radian is equal to pi multiplied by the unknown value, which is name it x, which is pi x. X is degrees, because 100 here we are talking about degrees. So divide the both sides on pi. Pi, it is just a number, 3.14. So pi will go with pi. Then x, which is 1 radian, is equal to 180 over pi. It will be approximately 57.3 degrees. This is 1 radian. So this is equal to 1 radian. So on the xy plane, this is x, this is y, this is 90 degrees. The half of this angle is 45. This angle is 75, a little bit more than 45. This is 7.3. This is 1 radian. Okay. This is 2 radians. This is 3 radians. The total angle is almost 6 radians or 2 pi. Also, we have some important angles in radians. Important angles. As we know, this is 0, this is 90, which is equal to, this is pi, or 180. 180, the half of it is 90, which is pi over 2, which is 180 over 2. Okay, we have, this is 60 degrees, and this is 30 degrees. 60 degrees, how much is it with respect to pi? 60 with respect to 180, how much is it? It is a third. It is equal to 180 over 3, which is pi over 3. So 60 degrees is equal to pi over 3 in radians. 30 degrees is equal to pi over 6. Right? What about 45 degrees? 45 degrees, it is half of this. Half of 90, it will be equal to pi over, not 2 over 4. Right? So we have 0, pi over 6, pi over 4, pi over 3, pi over 2, pi. This is 2 pi, because it is 360 as we talked from before there. Here, this is pi over 2, and this is pi over 2, and this is pi over 2. 3 times, we have 3 pi over 2, which is 270 as we said from before. We have 3 pi over 2 here. And we can use sine pi over 6, sine 2 pi, and so on. But we need to be sure that our system, the system or the settings on the calculator here, because many of the students did a mistake when they didn't change the system between degrees and radians, and find a wrong numerical values. So sine pi, which is sine 180, which is 0, sine pi over 6, which is half, which is sine 30, and so on. Any question about that? Okay. Also, many times in the previous we compute the circumference. if I need to measure this angle, this is plus 5 over 2 or plus 90. If I need to measure this angle, it is negative 5 over 2 or negative 90. The measuring of angles with the direction of counterclockwise. So in this direction, this direction is positive, and this direction is negative. So this is 2 pi. This angle is 2 pi, but this is negative 2 pi. Okay. If I need to compute the velocity in this direction, it will be positive, but the velocity in this direction it will be negative, and the accelerator is slow. We tried from before to compute the circle circumference. For example, this is circle. Okay. Any circle or any curvature has radius. The circle circumference is the distance rotated around from point to the same point, the total rotation. How much the angle in this direction? It's 2 pi. So the circumference S is simply equal to the angle in radians, which is 2 pi, multiplied by the radius, which is R. Okay, what if I need to compute this sector? Or, for example, this sector, just this sector. Okay, I need to know this angle theta in radians. Also, I need to know the radius R. So, delta S, which is this section, this curvature section, delta S is equal to theta or delta theta radian multiplied by R. Okay. If theta goes to 2 pi, then I have the total path, which is 2 pi R. Okay. And the same for the area. I know that the area is equal to pi R squared. If I need to compute the area of this, let us name it delta A. It is simply R pi, but I will not use pi. Pi is half. I have 2 pi. 2 pi divided by 2, it will be pi. Then I will have theta over 2 multiplied by R squared. If I use this, S is equal to theta multiplied by R. Integrated with respect to R, if I name it ds equal to theta dr. If I like this will be R squared over 2. R squared over 2. This will be area. Okay? But S is equal to theta R, and the area is equal to theta over 2 multiplied by R squared. These important relations to use in this material in the future. And I will remind you anytime you will face them. Okay. If we have now, any question about anything? Any questions online? Okay, now if we have this is the 0, the reference point or the reference angle of S, which is 0. This is theta 1. This is theta 0 equal to 0 at time t0 equal to 0. This is at t1. This is another theta 2 at t2. This is theta 1. This is theta 2. Maybe we have also theta 3 at time t3, and so on. These are angular positions. Remember that we have from before x0, x1, x2 position. Okay? And these positions changing with time. So because of that, we have T1, T2, T3, and so on. Okay. What if we have change in position with respect to the change in time, which is the rate of change in position? What we can name this thing from before? Remember that delta x over delta t. What is that? This velocity. Now that was before. Yes, now it is the velocity. Now we have changed in angular position. We have changed in angular. And the time is the time. The change in angular position means angular position later, which is theta 2 minus theta 1, or theta final minus theta initial over t final minus t initial, which is delta theta over delta t. So this is a change, a rate of change in angular position. This will give us a velocity, but this velocity is angular velocity. This will be equal to angular velocity. This angular velocity will not be named by the symbol v. We will name it omega. We know this is the capital case of omega, but we will use this omega. This small w, it is omega. Okay, so the angular velocity is equal to, which is omega. What is the unit of the angular velocity? We will look at the formula, theta in radians, time in seconds. So its unit is radians per second. We know from before that we have V is equal to delta x over delta t, which is meters per second, which is change in linear position over the time, the change in time. Now we have angular. So we have the velocity or the angular velocity. Omega is equal to delta theta over delta t. This is the same. Remove this, put x, it will be delta x over delta t. Okay, previously we know that the acceleration is equal to delta v over delta t, meters per square second. We know that. This is the average because it is delta over delta. What if we need to find the instantaneous? It is simple. Omega instantaneously is equal to the limit when the time period goes to 0 of delta theta over delta t. It will be equal to d theta over dt. This is the angular velocity instantaneously, d theta over dt. We know that from before it is equal to dx over dt. Right? Also the same for the acceleration. It was dv over dt or the second derivative of the x with respect to time. We derived the x position 2 times to find the acceleration. You applied this many times. Okay, so if I am talking about the acceleration, linear motion, does that mean that we have acceleration in angular motion? Yes, we have the acceleration or the angular acceleration is equal to delta omega over delta t, which is average value, and the sample of the acceleration is alpha. Alpha average, I think we talked about it before when we talk about v square over r and the planet's rotation. This is delta w, I'm sorry, delta omega over delta t. And alpha instantaneously is equal to the limit when the time period goes to 0 of delta omega over delta t, which is d omega over dt. And again, omega is the first derivative of the angular position. This will be equal to d2 theta over dt squared. Any question about that? Look, I am now just redefining a simple thing. We see like this thing from before. We see x, y, z, v, acceleration, and so on. But I put new names for a new kind of motion. Look, this is a new kind of motion. It is not like this. This is just in x direction. But now we have this motion. And we will use the same set of formulas. We will use the same velocity way to compute the angular velocity and the angular acceleration. And we will use the equations v2 is equal to v1 plus at and so on. And as always, we will see many examples. Any question about that? Flying. Now, we have the linear and the angular. We have the position, it was x, but we have it theta now. This is in meters, but this is in radians. The velocity is delta x over delta t. This was meter per second. But now the velocity omega is equal to delta theta over delta t, which is radians per second. Until now we have acceleration, which is delta v over delta t, which is meter per square second. And now the acceleration alpha is equal to delta omega over delta t, which is radians over square second. Okay? We just stopped talking about these things, but in angular motion. I think I have an example now. This is theta 1 at T1. This is 0. And I have another theta. This is theta 2 and T2. And also we have another theta. This one. This is theta 3 and time T3. We have a velocity from here to here. We have omega 1. We have another velocity from here to here, which is omega 2. And we have a third omega. Just like before, we find V1, V2, V3, and so on. Now, if theta 0 is equal to 0, radians, and T0 is equal to 0 seconds. Theta 1 is equal to pi over 6, which is 30 degrees. And T1 is equal to 1 second, I think. Theta 2 is equal to pi over 3. And the time there is 3 seconds. Theta 3 is equal to 2 radians. And the time is 8. Now to find theta 1. This is pi over 3, which is 30 degrees. But how much this angle in radians? It is simple. Pi, it is 3. Wait, where's the it's working. Okay. Pi over 3. No, it is not 30. sorry, 60. We know from before 1 radian is equal to 57.3. So this angle is more just more than 1 radian, which is pi. Where's pi? 3.14 over 3. It is equal to, this is theta 1, which is equal to 1.05 almost radian. This is 60 degrees. Theta 2, which is pi over 6. No, this is pi over 3. Okay, this is theta 2. I did something wrong. This is theta 2, yes. This is theta 2. Theta 1 is pi over 6, which is 30 degrees. Pi over 6 is equal to 0.52 radians. This is theta 3. It is 2 radians. Theta 3 is equal to 2 radians, which is 57.3 multiplied by 2. It is 114 degrees. Okay, what we need to do? We need to calculate the velocities, the angular velocities. Here. Okay. Let us compute omega 1. I'll remove these things. Just to know, omega 1 is equal to delta theta over delta t, is equal to theta 1 minus theta 0 over t1 minus t0. This is theta 1 pi over 6, yes, minus 0 over the time period, which is minus 0. It will be equal to pi over 6, which is equal to 524 radian per second. This will be equal to 0.524 radians per second. Radian per second, it is a velocity. What about the second velocity? From T2 to T3? Yes. Omega 2 is equal to theta 2 minus theta 1 over T2 minus T1. This is equal to theta 2 is pi over 3 minus theta 1 pi over 6 over T2 is 3 minus the time initially was 1. This will be equal to pi over 6. No, I converted them here. You can see them in the notes. This will be equal at the end to 0.26 radians per second. It's another velocity, different than this one. The angular velocity now is changing. That means we have acceleration. And we can compute that acceleration. Okay, what about omega 3? It is omega 3, the velocity from here to here. It is theta 3 minus theta 2 over T3 minus T2, which is equal to how much the angular position now? It is 2 minus pi over 3. 2 minus pi over 3 and over 8 minus 3, which is 5. This will give us a new velocity. It will be to 0.19 radians per second. This is another velocity. We have 0.52, 2.6, 19%. Is the velocity, the angular velocity now, is it increasing or decreasing? Decreasing. It is the same question that I asked before in the linear motion. What does that mean about the acceleration? Is the particle now, or the rotated body now, is it rotated with acceleration or deceleration? Deceleration. It has a negative acceleration, right? Not a positive. Because how can we compute the acceleration? It is V2 minus V1 over T2 minus T1, right? We just take delta V over delta T. V2 minus V1, it is negative value because this one is smaller than this one. So we have negative angular acceleration. After a while, this object will stop, will not move because, for example, I move it like this. It is moving, then stop. Or like this. And like this. It is moved, then has negative acceleration, then stopped after an angle theta. We can use the equation of motion, V2 equal to V1 plus AT, V2 squared is equal to V1 squared plus 2AX, and so on. We can use them in the angular motion. And we will apply them. Any question about the example? There is a note. Previously, I'll draw it. Previously, when we have a linear motion, all the parts of the stick are moving with the same velocity. Okay? But now, look, when we are moving, the velocity of the end of that stick is, the velocity there is faster than here. Because we have a different radius. I'll make it cleaner. For the rotated objects, the object which is near to the center of rotation, like this one, for example, is slower than this object because the distance moved here is less than this. So the velocity or the speed of the points on the rotated object, not all of them on the same speed, because they have different distances from the rotation axis, right? So if there is a door and you have to be hit by it, you are hitting this point, it will be faster. The door will be faster than this point. So your hit here will be affected on you more than this point because it has more velocity and more momentum. By the way, we have angular momentum also. Okay. Any question we have done today? We will, in general, we will use the same formulas from before, but in angular motion. Any questions online? Okay, thank you.